adaptive algorithms. He's the one who was dynamic regression. He's one of the dynamic regression. Was that your student sitting next to me? Yes. Was that your student sitting next to me?
Haven't seen him at I'm going in Thank you. I've seen him already. Yeah, he was behind. He was
Okay, welcome everyone to the second afternoon session. And the first talk in this section is going to be given by Srikant from UIUC on clustering using pairwise comparison. Thank you.
This is a joint work with Barbara Dembin, who's a student at Ecole Polytechnique, who visited me earlier this year, and Siddharth Satpathy, who's somewhere here. Where is Siddharth? Oh, there he is. Yeah. So if you have any hard questions, you can ask him. If it's an easy one, ask me, please. So this builds on joint work with another former student, Rebu, and a bunch of my colleagues. So the outline of the talk is I'm going to talk about what I consider the traditional noisy pairwise comparisons problem. And I'll talk about what our problem is, and I'll talk about the algorithm and the prior work that I mentioned, and what is new in this talk. So the traditional noisy pairwise comparisons problem is this. So let's say you go to Amazon's website, and sometimes they might show you 3 cameras, for example. You're searching for something else. Maybe you're searching for cameras, but they'll just show you a bunch of cameras. So Amazon probably has like thousands of cameras in its store, and they show you some of these cameras, maybe 3, sometimes even 2. And then let's say perhaps you click on the middle one, or you buy the middle one, you click on the middle one, and then so Amazon gets some information about you. They know that you like item 2 perhaps better than item 1, and item 2 also more than item 3. So the goal is to infer information about user preferences based on this limited amount of information that you have. Okay? So often it is assumed that the reason people click on a particular item over another item is that there is some underlying model. So for the talk that I'm going to give today, this underlying model is not that important, but just for completeness, I wanted to mention this. So there is something called the Bradley-Turing model that people use widely. So each item is associated with what is called a score theta, and the probability with which you click on item I over item j is proportional to e raised to the power of theta. Okay? And the goal is to estimate the vector theta from the pairwise comparison. So you show these pairs of items to many different people, and then you want to infer sort of the rankings among these cameras. You want to know who has the highest theta, who has the second highest theta, and so on. And one way to do this would be to just estimate the theta itself directly. And the information that you have is in the form of a matrix. This is important for what I'm going to talk about later. So for each user, so you have this matrix where if this user was shown items 1 and 2, then if there's a 1 here, that means the user preferred item 1 over item 2. If there's a -1 here, for example, this user preferred m over m minus 1. Okay, so you have this matrix, and a 0 means that you don't have any data about that position. Okay? So based on this information, the goal is to estimate the vector theta. Okay? Assuming that there is some underlying model here. And this is a well-studied problem. One of the earlier papers from 12 years ago is by Hunter, who showed that the solution to this optimization problem is the maximum likelihood solution to this problem. And more recently, Negaban O and Devavrat Shah have come up with an improved algorithm. And I recently found out just in the last 2 days that there is work by a different Shah, not the same Shah, Nihar Shah and Martin Wainwright on this problem where they don't even make any assumption like the Bradley-Terry model. Okay, so it's a non-parametric estimate of just the ordering of the items. Okay. So the problem I'm going to look at is a bit different. So I'm going to assume that different types of users have different score vectors. So perhaps users in the world are of 2 types or 10 types. Users of type 1 might like camera 1 more than camera 2 more than camera 3, whereas users of type 2 might like camera 2 more than camera 3 more than camera 1. Okay? So each user within a cluster has a different Bradley-Terry parameter. Okay, so if you want to think in terms of the Bradley-Terry model, although that's not important for what I'm going to talk about, so you can think that each user in each cluster, users in different clusters have different Bradley-Terry parameters. So they have different rankings of their of the various objects. Okay. So the regime we are interested in is where the number of users and the number of items is very large, like in Amazon's case. And I'm going to assume the users are in R clusters, where R is some constant, although I think you can probably let it grow slowly with respect to N or M. And as I mentioned here, the model now, in addition to the theta being a function of the object, it also is a function of the cluster that a user belongs to. Okay? And the goal of this problem is to make inferences where the probability with which a pair of items is shown to a user is very, very small. Okay, so you don't get to see all the objects. I mean, you might go to Amazon's website a few times a year, and then you get to see a few pairs of items. So the idea is can you infer the information that you want from just a few pairs, from giving your preference, or Amazon collecting preferences about just a few pairs of items. So in this matrix formulation, now again I have plus ones and minus ones indicating. So if the plus one here says that this person likes 1 more than 2, and this minus one here says this person likes 3 over 2. But now for example, there are 2 clusters. There could be R clusters. Yeah?
Do you know the clusters, or is your job to find the clusters?
Yeah, this is the problem. This is how it is in reality, but you don't know. And so you have to infer the clusters. So that is the problem. The problem is you're given the matrix, and you have to figure out who belongs to what cluster. Yeah?
How many as well?
Automatically. But we make some assumption we assume that the number of users in each cluster is roughly equal, but that's for the theory, and then we have some simulations with semi-real data. It's hard to get pairwise comparisons data. We took movie lens data and sort of converted to pairwise comparison data and then did some experiments, but I'm not going to show it here. I'll be happy to talk about it offline. Yeah. So the goal is to infer this, but you don't know who belongs to what cluster. All you are given is this matrix. Okay? Is the problem clear? So we are interested in 2 questions, of course. So the first question is, what is the minimum? Is there a fundamental limit to the minimum number of samples that you need? So the minimum number. So in this matrix, for example, the zeros indicate that this pair of items was never shown to this user. So the 0 indicates that. So you want to get an idea of how many zeros can I have in this matrix and still cluster the users correctly. So that's the lower bound. And of course, what is really more important is that what algorithm am I going to use to achieve this lower bound? And I'm going to answer these questions in the reverse order. First, I'm going to give you the algorithm. Then if I have time, the lower bound is actually very trivial. Okay? So first, I'm going to talk about an algorithm that we designed a year and a half or 2 years ago. And that forms the nucleus of what I'm going to talk about. And then we have made a substantial improvement to it, at least theoretically, and which is the main new result. So the key idea is to first take this matrix of pairwise comparisons. So suppose there are 4 items, okay, and 3 users. There are 4 choose 3 pairs of items that you can show, right? And so if there are 1,000 items, then there are 1,000 choose 2 pairs. So it becomes 1,000 squares. If there are 10,000 items, then the number of pairs of items is 10,000 square. So the number of columns in this matrix is just exploding. It's becoming much, much larger than the number of items. And that leads to a lot of noise. So what we do is first convert this matrix into what is called a netwin's matrix. So I'm converting a matrix with m choose 2 columns to m columns. And the way I do it is that for each item, I just simply compute the total number of times this user ranked item 1 over everybody else. So for example, this user ranked item 1 over 2, and then that's it. So it's just 1. Whereas 2, for example, was rated. I guess I need to find where there's a total. Okay, let's look at item 2. Item 2 was ranked lower than item 1 here. It was ranked lower than item 3 here, but was ranked better than item 4 here. So the net number of times item 2 won is -1. Okay, so I'm converting a matrix with n users and m choose 2 columns of pairwise comparisons to an n by m matrix. So this is the first step. And this leads to a tremendous noise reduction. If we try to do clustering directly on this matrix, it gives very poor performance. And then what you do is first convert it to this netwin's. Okay?
Might not be -1 +1.
Yeah, I don't know why we chose this. This could be any number. It could be 5 -1, but the row sum will be equal to 0. Right. Because if somebody wins, then somebody else has to lose. The row sum will be 0, but it doesn't have to be minus. This will be +1s and -1s, but these don't have to be +1s and -1s. You're right.
Why would if you go back to the last one, on the left-hand side, why does it have to be 1 -1? Can't it be that
you could show the same item multiple times to a user, but we are in this. I don't think that'll change anything. We're just assuming that you just shown it once. Yeah, it does that. That doesn't make a big difference. Yeah. So I've already said this. So the basic idea of the netwin's matrix is that it takes an n by m choose 2 matrix into an n by m matrix, and this actually has a tremendous noise reduction. You can think of it in terms of increasing the SNR or whatever, but essentially it makes the data less noisy. Okay? And then after this, all we do is spectral clustering. It's pretty straightforward. So since there are R clusters in the matrix, if you look at the expected netwin's matrix, there are only R independent rows. So this matrix will have, if you know the expected value of this matrix, then it will have R non-zero singular values. But what we have is a noisy version of it. So it'll have R singular values. For example, if R is 10, it'll have 10 singular values that are large, and the rest will be small. And then you take the original matrix, set X all but the first R of them. This is something spectral clustering that many of you probably know. Just set the rest of them, the rest of the values equal to 0, singular values equal to 0, and then do clustering on the resulting matrix. Okay? And the main result in the previous paper is that if the number of pairwise comparisons per user is R squared log cube of n, then all but k over n fraction of the users are misclustered correctly. So positive, yeah.
So that means how does R depend on the data?
We're just assuming there are R clusters yeah. So and you can see how many clusters there are by just looking at the number of singular values. You'll see a phase transition. You'll have a lot of singular values that are large, and suddenly there'll be a bunch that are very small. Yeah. In the movie lens data, there was 3 or 4 clusters. How much? 4 clusters. Yeah. For example, you can clearly see a sharp transition. So the main result in the previous paper was the number of pairwise comparisons that you need for each user is R squared log cube of n. And if you have this many pairwise comparisons, then all but k over log n fraction of the users are misclustered. At most k over log n users are misclustered with high probability. A positive spin on this is to say that this fraction of users that are misclustered goes to 0, but it goes to 0 at rate 1 over log n, which is very, very slow. Huh?
What was K?
So some K, some constant K is what I mean. Yeah. Some constant, yeah, sorry. And on the other hand, if you don't want any users to be misclustered at all, so you want to cluster all users correctly, then suddenly using the algorithm that I just described, at least theoretically, the number of comparisons that you need, number of pairwise comparisons that you need per user is actually proportional to the total number of users. So you need a huge number of pairwise comparisons, which is totally unrealistic. And the goal is, can you prove that perfect clustering is possible with far fewer comparisons than this? Our new result doesn't have this n here, which is quite spectacular. So you just get rid of the n and by adding one more key step to the process. Okay. So the key step was inspired by a paper by Van Wu from 2014 on community detection, which is somewhat of a different problem. Here, the one thing is sometimes this term pairwise comparison can be confusing. People often assume that I'm comparing users directly. I'm not comparing users directly. Each user is giving a bunch of pairwise comparisons about items. So all I have about each user is some metadata. So I don't have a direct comparison between users. So whereas in the community detection problem, if you know there's a graph, and users within the same cluster have a higher probability of forming an edge amongst themselves, and users across clusters have a lower probability for forming edges amongst them. So there's an edge or a lack of an edge between every pair of nodes. I don't have any such information here, but nevertheless, there is an interesting idea in this paper that we sort of used in our problem. The idea is very simple. So all you do is you split the item. Suppose there are 1,000 cameras. Okay, you split them into groups of 100. So I'm going to use information about 100 cameras and the pairwise comparison about those 100 cameras, and then the next 100 cameras and the next 100 cameras and so on. And I'm actually throwing out a lot of information. So I'm not using pairwise comparisons about the first group of items and the second group of items. This is somewhat surprising, and actually this improves the answer. And the basic idea, okay, so I'll get to the why this works later on if I have time. And then what you do is that you do clustering based on this smaller amount of information, and then you pull the information together. And the way you pull the information together is that user 1 might be in cluster 1 in 4 of the subsets of data, and might be in cluster 2 in 3 of the subsets of data. Then you say that user 1 belongs to cluster 1. Okay? So the idea is that you do majority voting. So I'll go through the details. So basically, the idea is that you take the items, split it into smaller groups, do clustering based on the smaller set, and then do majority voting. It's some sort of maybe can be thought of as coding in some sense. Okay? So there is error in each little set of data items that you're looking at, but when you do majority voting across the entire set of data items, it actually produces the correct answer. So visually, this is the algorithm. So I have in this example, I have 6 items. I'm going to split the data into 2 parts. I'm going to only look at pairwise comparisons between items 1, 2, and 3 here, and pairwise comparisons between items 4, 5, and 6. Okay? And then I do what I said earlier. So you just do the net wins matrix for this, net wins matrix for this, and then do spectral clustering. Okay? So items 1, 3, and 4 might partition the users. There are items and users. So the partitions here refer to the users. The users are then clustered like this. So each one of these items might reveal a different clustering of the users. Now the question is which one of these to believe. Okay? And first of all, I don't know how cluster 1 here or partition cluster 1 here, how do I know which cluster here is the same as this cluster here? So it's not even clear. For example, this partition consists of a certain number of clusters. This partition consists of yet another set of clusters. And this partition might contain items 3, 4, and 5 in the first cluster. And this partition might contain item 4, 5, and 6 in the first cluster. How do you decide which cluster in the first partition corresponds to which cluster in the second partition? We just simply do a majority vote again, something like a majority vote. You look to see if this cluster overlaps the most with this cluster, then you just say that these 2 clusters must be related. Okay? Once you identify, so basically the idea is that, okay, so if this part is confusing, just assume that basically the algorithm produces clustering. So there is some additional step to make sure the clustering is consistent in some sense. But the next step is the key step. So the key step here is that if user U belongs to this cluster, this cluster, this cluster, and this cluster, so you see that user U belongs to cluster 2 in 3 of the partitions and cluster 1 in 1 of the partitions. So I'm just going to use a majority vote. Okay, I'm just going to say that user U belongs to cluster 2. Okay? So the algorithm is this, again, just to summarize. You take the cluster, you take the items, partition them into L sets, where L is something that we'll specify in the theorem. And then for each of these L sets, using information from each of these items, the items in the first set and the items in the L set, basically cluster the users. Okay, cluster the users based on this limited amount of data, and put the answer together by just simply doing a majority vote. Okay, so again, if there are 1,000 items, what I do is, and if L is 10, I look at information about just the first 100 items, and the second 100 items, and the third 100 items, and do a clustering of the users based on less data than what I am given. Okay, and then I do a majority vote. Okay, so I throw out some data, actually, and I do a majority vote. And the result is that, the previous result was that you need n r squared log raised to the power of log raised to the power of 5n pairwise comparisons per user to cluster all users correctly with probability at least 1 minus 1 over n. And now this n is gone here. Okay? Yeah.
So I guess I'm surprised that there isn't some dependence on some notion of how different the users in the different clusters are. I mean, in some sense.
Yeah, so I will specify that. So exactly. Very good point. Yeah. So you need some assumptions for this theorem to hold. And since I have a few minutes, I'll just go through the proof and I'll tell you exactly what assumptions we make. Okay. So the assumptions we make is that the average ranking, the expected value of the rows are sufficiently separated. And this is true so we don't need the Bradley-Terry model for our result. But if you assume that the model comes from a Bradley-Terry model where the thetas are chosen at random from some interval, then you can show that this condition is satisfied with high probability. Yes. So that is a very good point. So the basic idea is that the cluster should be, the first step is to argue that the clusters are well separated. Either you can make that as assumption, or you can assume an underlying probabilistic model under which this assumption holds with high probability. That is the first step. Okay? And then the next step was to show that the rank R projection of each row is actually close to the expected value using some concentration inequalities. You can show that this happens with, again, this happens with high probability. So basically here, if you notice that the rows are separated by order n, and the noisy version after it's projected actually is only separated by log n. So these are sufficiently well separated. And the idea is that if you have enough number of measurements, you can get a bound on how well they are separated. Okay, so in the previous, the first version of the result, we assume that you have enough measurements, and so they're very well separated, and then you get the answer directly. So what we do is here now we don't assume that there are enough samples for them to be well separated. So all we are able to show is that the probability of misclustering is delta, which doesn't go to 0. Okay. On the other hand, once you do split the items into L sets and do a majority voting, then it's a straightforward Chernoff bound argument to show that the probability of misclustering actually goes to 0. So for this, you need to choose L, which I haven't specified so far. L has to be chosen as order of log n. Okay? Yeah?
So if you don't have that separation assumption at the beginning, could you do something like determine the number of clusters like online together with this algorithm? Because it seems like you want to define clusters. The notion of cluster should exactly be that there's a separation between clusters. So if you use that as your definition, could you adaptively discover the correct number of clusters?
So in the actual algorithm, the way we determine the clusters, we just look at the singular values, and there is a sharp transition actually. So yeah, at that point. We haven't tried to justify that analytically, but it's quite clear that in the movie lens data, for example, the fact that there are 4 clusters is quite clear. There's a bunch of singular values that are large, and then it just suddenly drops to something very, very small. And you can see that there is a phase transition there. In the previous paper, we did something else. We used what is called, people call it the elbow method. So basically, you assume that there are 2 clusters, 3 clusters, 4 clusters, and see how much improvement that you have. And the improvement in performance is dramatic up to some point, and then it starts tailing off, and then you assume that that is where it is. So but though we don't have theoretical guarantees on it. So the way the theory is right now is that, so we assume this, but we also justify it in the sense that if you use the Bradley-Terry model, and the thetas are picked at random from some uniform distribution, then this is satisfied with high probability. That's the way we justify it. Yeah. So the question is that, how close is this to a lower bound? The lower bound is really very easy. So if you have two users from two different clusters and neither of the users has been shown any pair of items at all, okay, then of course you cannot cluster. You can't tell whether these two users belong to the same cluster or they belong to a different cluster. And so then you can easily figure out the probability with which I need to show a pair of items to a user cannot be any smaller than log n over n square. What did I say before? And you can so this is within a polylog factor of the minimum number of so the number of pairwise comparisons you need per user is log n over, this is the probability with which you need to show a pair of items. Since there are n choose 2 items, so the number of pairwise comparisons that you don't need to show per user is of the order of log n. And our result here says that the number of pairwise comparisons for our algorithm is log power 5n. So it is within a polylog factor of the optimal. Okay, is that clear? So that's I'm just summarizing the main result here. So if more than r log raised to the power of 5n pairwise comparisons per user are available, all users are clustered correctly with probability at least 1 over n. The number of comparisons required is within a polylog factor of the lower bound. And it's been asked twice. I think the key assumption you need is that the rows in the expected matrix are well separated, which is the only place where we use the Bradley-Terry model to justify it. The rest of the results don't actually use the Bradley-Terry model at all. Okay? So there is some related work. The work that we use the most is this paper by Van Wu on the stochastic block model and clustering in it. And so what I'm saying in this paper is very similar to what Van Wu says in the paper. So basically, he starts off with spectral clustering, and he says you cannot prove that spectral clustering actually works. So he does a different kind of partitioning of the data, and then does something like a majority vote in his paper also. And he shows that works, okay, that achieves some kind of a basic limit for when spectral clustering would work. But what is unknown, and that's also true for our paper, and I want to be clear about this, that it is not clear that the second step is needed. If you do simulations, it looks like you can directly just do spectral clustering and it works. Okay? But theoretically, we're not able to prove that just directly applying spectral clustering to so the first step is important. So you have to first form this thing called the Netwins matrix. That is important. But you can directly do spectral clustering on the Netwins matrix, and it seems to work in simulations. But we are not able to prove that actually is within the sample complexity of that is within a polylog factor is not clear. Yes?
What kind of data are the simulations on?
So this I didn't think that I would have time, so I didn't include them here. So the data is movie lens data. So it's impossible to get pairwise comparisons data directly. So what we do is that you take actual numerical ratings that people give, and then we say that if you have rated a movie 2 and another movie 3, then you're more likely, if I show you movies 2 and 3, then you're more likely to rate the second movie higher. And then we make a sort of a Bradley-Terry kind of, so we use those 2s and 3s as the parameters of the Bradley-Terry model. So it's sort of a pseudo-real data. I don't know how to get pairwise comparisons data otherwise. Yeah. So we took the movie lens data and sort of converted it to pairwise comparisons. Yeah. I have to apologize to Avram Bloom because it's the second time he's sitting through this talk. Unfortunately, I just gave this talk 2 months ago at another workshop. So this is my last slide. So we've presented an algorithm to achieve perfect clustering with high probability, where the information that you need for clustering comes from this metadata about pairwise comparisons of items. So users are not directly compared, but they are compared through these rankings that they provide to other items. And majority voting from spectral clustering over different data partitions, this idea inspired by this Van Wu paper, is the one that at least theoretically works. The open question is whether without doing that, whether it directly works is something that we don't know yet. And at least if you do that, we can show that we get within a polylog factor of the sample complexity lower bound. That's it. Thank you.
be fair that so you're losing some information by constructing this sequence matrix, and this partitioning is allowing you to retrieve back some of that information, and which is giving you this.
Well, I think the netwinds matrix that is actually important. I don't think we're losing information. Actually, that is more like an SNR. So there is a it is actually. So if you want to estimate a high-dimensional random vector, often you have to, and you're getting information about a low-dimensional quantity, projection can be useful, and that step is very much like a projection. So I don't think you're losing any information there, but the later part is somehow, it is sort of like coding. That's the best way that I can describe it. So you're allowing some errors, but instead of directly estimating something, you're sort of getting information about it from many different perspectives and sort of putting it together. So it's sort of like coding, error correction codes, but it's not fully clear to me. Yeah, that's the question.
Yeah. So where do you need R to be a constant? Like, is it just to have a separation?
So these are all high probability results. So there is 1 minus 1 over, and there's so many places where and you can make. So I think R something like log n would work, but I think then the rate at which you're going to 0 will be slower, and there is a lot of leeway here. So if I change some assumption, then it might lead to slower convergence. But if I want 1 minus 1 over convergence, there's a concentration inequality at some point, for example. So there are many places where we use union bounds over clusters and so on. So there you get a multiplication by R, and instead if it is a function of n, then you'll get a multiplication by function of n, and then you have to take that into account. Yeah.
And did you say that you assume that the clusters have the same size, more or less? You said
the more or less, yeah. So that's the other. Yeah, that's what. Yeah, it's more or less in the sense that as long as they are all, they all grow linearly with respect to the total number of users, it's fine in theory. But in the simulations, what we noticed is that in the movie lens data, the 4 clusters are of widely different sizes. Do you remember what the cluster sizes were?
Out of 1,000 users. There are like 500, 100, 200, and 100.
Yeah, so there could be like a factor of 5 difference, for example.
Where do you need this assumption? Where do you need it?
Again, just various bounds. I mean, so you use a concentration inequality to show that the projection is actually close to the expectation, okay? And then you have to say this about all users. I mean, so you have to make sure that if you want to cluster all users correctly, every one of those users must be closer to its cluster average. And the clusters have to be roughly equal size for this to work out. Yeah.
Maybe in the interest of time, we'll take questions offline, and thank you.